Okay. So, sorry, we were talking about the limit as x goes to infinity of our function. And our function in this case happens to be 5x plus 2 over x minus 4. So we could try a direct substitution. If we thought about x getting very, very large, infinity, the 5x really dominates this term in the numerator, and so we would get some type of infinity divided by infinity minus 4, and we'd get some type of, quote, infinity divided by another type of infinity. Now I'm using quotes because infinity is not an actual number, it's a concept. But this is an idea of I'm trying to understand what would happen. But because infinities aren't equal, I can't say this is 1. So I need to think of a different way. Okay? So an alternative is to think about this. What if I asked about the limit as x goes to infinity, but let me alter every term in our function. The highest degree in the numerator is a first degree, and the highest degree in the denominator is a first degree. So let me try and divide through everything by x. That will be helpful because now I can reduce, and the x over x will cancel, and we'll get 5 plus 2 over x in the numerator, and down below we get 1 minus 4 over x. So why was that helpful to us? All right. So now let's try and think about doing this direct substitution and thinking about what might happen as x went to infinity. Okay. Well, if x goes to infinity, there is no x in this term, so the 5 must stay. Then plus, I would get 2 over some, quote, infinity. Down below, there's no x, so the 1 must stay, minus 4 over some, quote, infinity. Now remember, the infinities, I use quotes because they're not an actual number. But let's think about what was happening. If we take 2 over an extremely, extremely large number, say 1 billion, the number becomes very, very small. It's the same reasoning we had here. I took 1 over our x values, and as x went larger and larger and larger and larger, we could see that the function was going to 0. We can use that same reasoning here. 2 over a very, very large number is actually going to 0. And 4 over an extremely large number is also heading to 0. Which will simplify our problem to 5 plus 0 over 1 minus 0, which is just 5 over 1, which is 5. And this is equal to where we started from, the limit as x goes to infinity of our function 5x plus 2 over x minus 4. And this is the end behavior. And what that will mean for our function then is that as x gets extremely large negatively, or extremely large positively, we will have an asymptote, and that equation will happen at y equals 5. So just like our basic function, we have two asymptotes to deal with. And now we just need to determine the behavior of the graphs. So here the asymptotes were here, and now we've shifted it. I need to know, is the graph happening up here, down there, down there, down there? Since this is to be a function, the graph cannot live up here and here at the same time. So as a sketch of the function, I will take a value on this side to test it. Pick an easy one. I don't know. Say 5, because we get a nice number down here. Okay. So now I evaluate the function. At 5, which is 5 plus 2 over, so for 5 times 5 over 5 minus 4. Alright, so that's equal to 25 plus 2 over 1, which is 27. So what that means then is that the ordered pair 5, 27 is on the graph. Clearly, 27 is way above this asymptote line here. So we will label this point 527, and then from there we will just sketch it out that the graph is bounded by these two asymptotes. Now we also have the problem of, well, does the graph live up here or down below here? So to do that, we need to evaluate a point less than, an x value less than 4. And again, we'll pick an easy one. If this was negative 6, I would go to negative 10. So perhaps we'll try that one. F of negative 6. So inside of here, negative 6, negative 6. So this is negative 30 plus 2 over negative 10, which is negative 28 over 10, which is positive 2.8. Which means we get the ordered pair negative 6, comma 2.8. So coming over here at negative 6, the function only attains a value of 2.8, which is less than this 5. We'll say here, let's label the ordered pair 2.8, right? And then from there, we can just sketch in and infer that the graph will be doing something like this and be bounded by those two asymptotes. Let's try another example about how we would sketch these. Okay. So for example, let's look at f of x is equal to 3x plus 5 over x squared minus 4. We want to consider vertical asymptotes. And vertical asymptotes will occur when the denominator equals 0. So from here, x squared is equal to 4, and so we will get 2 asymptotes when x is equal to plus or minus 2. So let's label those in. We would also like to know if there's any horizontal asymptotes. So for horizontal asymptotes, we're talking about end behavior. And so we can ask ourselves, what is it that the limit of this function is as x goes to infinity of 3x plus 5 over x squared minus 4. Again, if we do some type of reasoning as far as what if I put a very, very large number in here, I'll get 3 times infinity plus 5, which is another type of infinity. However, if you put infinity in here, like if you take 1,000,000 and you square that, that becomes a much larger infinity. So I still don't know too much. So let's use our trick. And again, look about the limit as x goes to infinity, but this time I want to divide everything through by the dominant power. And the dominant power here is x squared. Now let's do some simplification. Okay. X goes into itself once and into x there. So in the end, we're left with 3 over x. Okay. There's nothing to simplify with 5 over x squared over, but now x squared over itself goes to 1 minus 4 over x squared. And now we can use our reasoning and think about what's happening. As x becomes very, very, very large, 3 divided by an extremely large number will go to 0. And certainly then 5 divided by x squared also goes to 0. Similarly then 4 over x squared must go to 0. So by our reasoning, we have the limit then. I'm actually going to take the limit is 0 plus 0 over 1 minus 0, which is 0 over 1, which is just 0. And that means we get a horizontal asymptote at y equals 0. Maybe I should put that in green. Because eventually that's going to be the end behavior. As x gets extremely large negatively, or extremely large positively, y equals 0. Okay, so that's just setting up this graph. Now we have some key points that we need to know. We always need to know, do we have a y-intercept? Okay. That will tell us a point on the graph. Okay. So to find a y-intercept, we let x equal 0. So that is, we are finding f of 0. So 3 times 0 plus 5 over 0 squared minus 4, or 5 over negative 4. So our y-intercept occurs at 0, negative 5 fourths. Okay? So this is our y-intercept. Now that's going to be helpful for us because then I know this point exists. I'm going to label it to make it true. This is just a sketch. Okay? So I know that point is there. But if we ask about y-intercepts, we should always ask about x-intercepts. So let's do that. Okay. For our x-intercepts, okay, you let f of x equal 0. Okay. So that is, we have 3x plus 5 over x squared minus 4 equals 0. You just do that. And now we can solve this. The problem is we have x's in the numerator and the denominator. We want to get x out of the denominator. So let's multiply through by that on both sides. What's nice then is these will cancel, leaving us with simply 3x plus 5. And nice enough, 0 times anything is still 0. So 3x minus 5 is equal to minus 5. So x is equal to negative 5 thirds. And what that means then is that we have an x-intercept at negative 5 thirds, comma 0. And when we plot that on our graph, it will be someplace here. And this can be a little disconcerting to students because this graph, this will cross its horizontal asymptote. And that's fine because it's what we call locally, it's happening in a very small area. Our asymptotes really are only talking about what happens at extremely negative values of x and at extremely positive values of x. So it is okay for a graph to cross a horizontal asymptote, but it will never cross a vertical asymptote. Now, if we wanted to go through this to complete this graph, what we would need to do is pick values. Say you could look at, say, negative 10. And what you would find then is that this graph would actually be bound down here. So this point would be negative 10 and the function evaluated at negative 10. I'll leave it to you to show that that happens. What we need to pick then is up here, say maybe positive 10, and evaluate the function. And what you would find then is it's someplace up here. And so we will infer that it's bounded by these. Okay, because we're just doing a stretch. But we're not sure what's happening in here. Okay, so this is the point about asymptotes. We need to pick values that are very, very close. Okay, so maybe like negative 1.9, kind of what's going on. And when you do that, you will find that it's a very large number. So it's taking off this way. Although there was no guarantee that it would. It could have gone down here. And also, we're not sure what's happening here. So we need to look at, say, positive 1.9. Because we don't know if it's going to go up or if it's going to go down. Actually, in this case, we do know it's not going to go up. Because if it was to go up, it would have to cross the x-axis again, which means I would have another x-intercept. Okay. So in this case, the graph is taking off downward like this. So graphs can do some very bizarre things around asymptotes. I'm going to stop the video right here and take a break, and I will be right